this video, we're going to continue talking about measures of spread. When data has a small spread, that means that most of the values will be close to the mean. When data has a larger spread, more of the data values will be far from the mean. So that's the whole point of looking at measures of spread. And one measure of spread that we look at is variance. It measures how far the values in a data set are from the mean, or the average. Now, in order to find the variance, we have to find just the deviation. The deviation is the difference between the population value, x, and the population mean, and recall that the population mean was mu. And so when we're talking about just the deviation, it's that value x minus mu. How far is that particular value from the mean? We can calculate population variance. And in order to do this, we follow these 5 steps. First, we want to compute the population mean, which remember is mu. After we've calculated the mean, we want to calculate the deviation, which is our x minus the mean, or mu. Then we want to square each of the deviations. That means take the x minus the mean, and we want to square that particular value. Now, here at step 3, the values will all be positive because you're squaring. And remember that if you square a negative, negative times negative becomes a positive. Then in step 4, we want to sum up the square deviations. That means to add them up. And it's also written, remember our sigma of our x minus mu squared. So we're going to add up all of those. And since we're looking for population variance, we're going to divide this sum that we just found by the population size, capital N. So when we're talking about population variance, it has its own symbol, which is the lowercase sigma squared. So this is our uppercase sigma, which means to add it all up. Our lowercase sigma looks like a 9 that's laying down. And that is going to be equal to the sum of the deviations, x minus mean, squared, and we're dividing by the population size. So this right here, remember, is for the population variance. And it's important to know the difference. So this is something you might want to put on your sheet of notations and everything, which is sigma squared, so that you will be able to identify it later, as well as use the proper symbols and notation while you're doing these calculations. When you're computing the population variance, it's very helpful to set up a table, and in that table, if you have one column of x, or your values, and one column with x minus mean, or your deviations, and then you have a column of your deviations squared. So in order to find population variance, it's the sum of this last column divided by your population size. Basically, how many rows do you have in this table? So let's look at an example of this. We're going to look at test scores. The data shown represents the scores of the first exam of all 10 students enrolled in introductory statistics. Compute the population variance of the test scores. Now we can identify this as a population because it specifies that all 10 students enrolled. So that key word there is all, helps us know that it's a population. In order to find the population variance, we must first calculate the mean, which, since we're talking about population, is mu. And remember that the mean is just adding them all up and dividing. So if I add up each one of these, and that means that I have 10 of them, so whenever I add these up, I get 790, and I'm going to divide by 10. So my mean, or my average, is going to be 79 for these 10 students in this statistics class. In order to continue working with this, I'm going to set up that table as I said, and the first column, remember, is just our x, or our values. And I already have them listed here: 82, 77, 90, 71, 62, 68, 74, 84, 94, and 88. I need to create my other columns. The first one will be for my deviation, x minus mean. So what I'm doing in this column is I'm going to take 82 and subtract the mean that we just found of 79 from it. So I'm going to take 82 minus 79, which is going to equal 3. And I'm going to do that all the way down. So I'm going to take 77 minus 79, which is equal to a negative 2. 90 minus 79 is equal to 11. And so you can kind of see where I'm at least getting these numbers. I'm going to continue on down. So 71 minus 79 is a negative 8. 62 minus 79 gives me a negative 17. 68 minus 79 gives me a negative 11. 74 minus 79 gives me a negative 5. 84 minus 79 is going to give me 5. 94 minus 79 is going to give me 15. 88 minus 79 is going to give me 9. So these are just our deviations. And overall, if we were to add up our deviations, they should come out to 0. And the reason why is because when we do the deviations, it's looking at how far each of these are from the mean. Now the last column that we set up is going to be our deviations squared. So I'm going to take this column and square each of its numbers. As I do that, I'm going to get 3 squared. 3 times 3 gives me 9. And notice I'm putting these in parentheses just so I can make sure that I take that negative 2 times a negative 2, which is going to give me a positive 4. So even in your calculator, when you're squaring negatives, make sure you put the negative inside the parentheses. Okay? And so 11 squared is going to give me 121. And I'm going to continue this whole method down. Negative 8 squared, which is negative 8 times negative 8, gives me 64. 17 squared is going to give me 289. Then negative 11 squared is going to give me another 121. Negative 5 squared is negative 5 times negative 5, so that's a positive 25. 5 squared is going to give me 25. 15 squared will give me 225. And 9 squared will give me 81. Notice all of these are positive. That is very important to realize that all of the deviations squared will be positive. I want to add this column up. So I'm going to take each of these, 9 plus 4 plus 121 plus 64, so that I can get the sum of the deviations squared. That means that I want to square them first and then add them all up. If you want to, pause the video and you try to add them all up. But in this case, whenever I add them up, I get 964. So these are my deviations squared. For population variance, we have sigma squared is equal to the deviations squared divided by our total number of data values. And so for n, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So n is equal to 10. Notice that's basically how many rows I have in my table here. So whenever I calculate this, I get sigma squared is equal to 964 divided by 10. So my population variance is 96.4. Now, the same rounding rule actually applies for variance as it does for the mean. We round to 1 decimal place. I want to caution you though on the rounding. Do not round off even the mean when you're computing the variance. So if the mean has more decimal places than you normally would round to, go ahead and keep all of them. This makes your data more accurate. And the same thing's going to happen when we use this variance in other calculations. When you're using a number in other calculations, you do not want to round. You always want to wait until the very end of your calculation to do the rounding. Now then, there's a difference between population variance and sample variance. There were not differences between how we computed the population mean and the sample mean, but there will be for computing the variances. Recall that we first need to compute the mean, in this case the sample mean, which will be x bar. Then we need to compute the deviation, which in this case is x minus x bar. Same procedure so far. Step 3 is we're going to square the deviations. Still the same procedure. In step 4, we're still doing the same procedure as x minus x bar squared. We're going to sum those up, add them all up. Step 5 is where we hit the difference. Instead of dividing this number by n, because we're talking about sample variance, we actually divide by n minus 1. That is our sample size minus 1. Now, there are reasons why we divide by n minus 1. The reason is because the deviations that we're using for sample mean tend to be smaller than the deviations for population mean. And we also want to discuss degrees of freedom. In this case, since we only have one variable that we're looking at, which is our value, x, our degrees of freedom are always, in this case, going to be n minus 1, which is what we are dividing by. Degrees of freedom deal with when we're talking about a sample instead of a population. So for sample variance, we use the same type of formula, except instead of sigma squared, we use an s squared. And then we have the sum of the deviations squared. And remember, we're going to divide by n minus 1 instead of just n. Again, it's the same procedure for population and sample. The only difference is wherever it comes down to the actual division at the very end, we're going to divide by n minus 1. So let's look at an example. So this is still talking about test scores, but in this case, the data shown here represents the scores on the first exam of 4 students enrolled in introductory statistics. So since we're talking about 4 students, this is going to be a sample. So we want to compute the sample variance of the test scores. So my first step is going to be to calculate the mean. So I'm going to take 90 plus 77 plus 71 plus 82, and I'll divide that by 4 because that's how many values we have. So I end up with 320 divided by 4. So our sample mean is 80. Once I have calculated my mean, I'm going to set up the columns just like I did for population. I will have an x for our values, an x minus x bar for our deviations, and then an x minus x bar squared for our deviations squared. So my values in this case are 90, 77, 71, and 82. I'm going to take the value minus the mean, so 90 minus 80 will give me 10 for that deviation. 77 minus 80 will give me a negative 3. 71 minus 80 will give me a negative 9. And 82 minus 80 will give me a positive 2. Notice if I add these up, that does equal to 0. Now I need to square these, so 10 times 10 will give me 100. Negative 3 times negative 3 will give me a positive 9. Negative 9 times negative 9 gives me a positive 81. And 2 times 2 gives me a positive 4. So I have now filled in my table, and I can look for, well, my n is 4 because that's how many data values I have. The other thing I need to do is to add up my deviations squared. So I'm going to take 100 plus 9 plus 81 plus 4, and that will give me 194 as the sum of my deviations squared. So whenever I go to put this in the formula for sample variance, remember that is s squared, I'm going to have the sum of the deviations squared divided by an n minus 1 because we're talking about a sample. So we're going to have 194 divided by 4 minus 1. So 4 minus 1 is going to give me 3. So s squared is equal to 194 divided by 3. So our sample variance will be equal to 64.7. And these are points because we're talking about exam scores. Notice in this particular case I rounded to 1 decimal because our values were whole numbers. If I tend to use this for any other calculations, I will not round. Now there's a problem with using variance as the measure of spread. Variance is computed by, we're squaring the deviations. This means that the values are also squared. So this is actually 100 points times 100 points squared. So it's actually, or I'm sorry, 10 points times 10 points. So that's actually 100 points squared, and so forth. we really want to look at measures of spread with the same units as the data. We can do that, and the way that we do that is through something called the standard deviation. We're still using the deviation. We will also still be using the variance. Standard deviation is a measure of spread. This actually has the same number of same units as the data. And it's found by taking the square root of the variance. So the easiest possible way, whenever we look at population population standard deviation, what we're going to do is, instead of saying sigma, and let me spell correctly, instead of saying sigma squared, we're actually going to just have sigma, because we're taking the square root. And so sigma is equal to the square root of the variance, which is sigma squared. So after we have found the variance, we take the square root of it, and this standardizes our deviations. This way we can compare and actually look at those deviations, or the measure of spread, a little bit better. Same thing happens whenever we're looking at the sample standard deviation. We're going to take the square root of the sample variance. And so instead of having s squared, we're going to have s, as I put an s squared up there. We're going to have s is equal to the square root of s squared. So again, I took the square root of my variance. So let's look at an example of this. Recall the test scores that we just calculated in the previous example for the 4 students. We want to calculate their standard deviation. Now, I said earlier, we do not want to round anything if we're going to be using it in future calculations. Therefore, whenever we look at this, our variance was equal to 194 divided by 3. I'm actually going to leave it that way so that whenever I do my calculation for sample standard deviation, which is s, I'm going to leave it, take the square root of 194 divided by 3. Most of your calculators, what you can do is just leave the 194 divided by 3 answer in your calculator, because that answer is actually 64.66666666. Okay? And so when we do this, if you leave it in there and you want to find the sample standard deviation, if you are using the recommended calculator of the TI-30 X2S, what you're going to do is you're going to have 194 divided by 3, hit enter, and then you're going to hit second, and then there's an x squared button. So you'll do 194 divided by 3, and then enter, and get an answer. Then you will hit second, and then the button that has this, the reason why is because it has this above it. Well, that gives you the square root on there. So then, in order to get the number that you just calculated, there's a couple of different ways. You can either retype the 194 divided by 3, or you can hit second and then the negative sign, which has answer written above it, ANS. So that means that we are using the answer that we just found. Again, you could have hit second, then your x squared, and then done 194 divided by 3, and then hit equals. Don't forget to hit the equal or the enter after you hit the answer here. And so we're going to get that the sample standard deviation is 8.04155871, which are all the digits that my calculator shows. Again, our data was in whole numbers, so I'm going to round it to 1 decimal place. And I'm going to say that the standard deviation is 8.0. Yes, please put the 0 on there. The reason why is that shows that it is a rounded number. Now practice some of the variance and standard deviation problems, and if you have questions, let me know.